Hi, in this video, we are going to do chapter 3, Vectors in Physics. So we are moving to two-dimensional motion, and we will first start with vectors, and then we will learn how to add and subtract vectors, and then we will do some two-dimensional motion problems. Okay, let's start. So in one-dimensional, so 1D means one-dimensional, in 1D motion, left and right can be represented with plus and minus, right? So instead of left, you can say minus, and instead of right, you can say plus. But in two dimensions, plus and minus are not enough. There are four directions: north, west, south, and east. So we have to use vectors for two-dimensional quantities. For example, velocity in two dimensions. So let me give you an example for a 2D vector. So this object with the vector sign on the top, it means this is a vector. So if you have a vector on the left-hand side of an equation, then equal sign, then you also have to have a vector on the right-hand side. So 3 is not a vector, 2 is not a vector, but what's vector here is x hat and y hat. These are two vectors, and we actually call them unit vectors. So the meaning of x hat and y hat is that they actually they help us specify directions. In other words, establish the coordinate system. So these are unit vectors. What it means is their length is 1. So here's x. So unit vector means, so hat means unit vector, so it's 1. And the length of y is also 1. So if their lengths are 1, then why are they useful? Because they show us the directions. This unit vector shows us the x direction, and this unit vector shows us the y direction. So if you now consider again this equation, so it says our vector is, it's 3 units in x direction. So so this is 1x, this is 1x, this is second x, and this is the third x. So our vector is 3x. So basically it comes all the way to 3, and it's 2 units in the y direction. So this is 1y, and this is the second y. So here you go, that's the 2. So you can think of this way: this r vector is composed of 2 vectors, which are, one of them is this vector, which is 3x hat, and the other vector is this one, which is 2y hat. So we will see in the future, in the next chapters, how they are useful, but you can think of this as, let's say there is some object here. So the person, let's say, pulling it, pulling it to the right with this much force, and the person here, the other person, is pulling it to the towards y direction with this much force. So the object would go in this direction. You can think of these the vectors like these. So okay, so let's continue. A vector has 2 properties. One of the properties is direction, the other is magnitude. So that means if you don't change the direction and the magnitude, then if you move the vector without changing its direction and magnitude, will not produce a different vector. So below are all the same vectors. So the direction is this direction, and the length is this much. Now, if you look at this one, this vector, they all have the same direction. They point to the same direction, and their lengths are the same. So the magnitudes are also the same. So these are all the same vectors. But if you have, let's say, draw another vector like this in the opposite direction. So the magnitude is the same with this one and with this one. Let's call it B. They have the same magnitudes, but their directions are different. So these are not they are not the same vectors. Even though the magnitudes are the same, but the directions are, not the same. Or you can have another vector like this in the same direction, which let's call C. Well, the directions are the same with A and C, but the magnitudes are different. C is definitely shorter, so they are also not the same vectors. Okay, so the point here is if you have a vector like this, and we will see in the next slides, we are going to do addition and subtraction. You can always move these vectors. I can move this here without changing the direction and the magnitude. So it will still be the same vector. Okay, so let's do some math. So let's say we are given this vector here, and also we are given this angle, 25 degrees. And the length of the vector, which is also, we also call it magnitude, it's 1.5 meters. Okay, so it's possible to write this as in this form. So to be able to write it in this form, we have to find the x component. So I'm going to call this, so let's say this component. So this is called r sub x. And the y component, and this is called r sub y. So how do you find, let's start with r sub x. This basically means the x component of the vector r. How do you find it? Well, you multiply the magnitude of the vector, not the vector itself, but the magnitude, which is a number. And so you multiply it with cosine theta. So this angle, so cosine of this angle. So it's going to be 1.5 times cosine 25, and it will give you 1.36. So this is 1.36. So remember, this is the hypotenuse. Okay, how do you find, so are you going to use cosine or sine to find this part? Well, this is adjacent to the this angle, so it's just here, adjacent to the angle. So you have to use cosine. And when it's opposite, this part, you have to use sine. So let's find this ry now. So this is the angle again, 25, and this length is 1.5. So you basically do 1.5 times sine 25, and you get 0.634. So this part is 0.634. Now, because I found the components, x and y components, now I can write it in this form. So this vector r is in the x direction for the magnitude of 1.36, and also in the y direction for the magnitude of 0.634. Okay, what about the magnitude? Now, the magnitude here is already given, but let's say you are given the components. Let's think about this situation. You don't know the magnitude of the vector, but you are only given the components. Can you calculate the magnitude? So can you calculate r? Of course you can, because you could easily use the Pythagorean theorem, where the hypotenuse is r, and this is ry, and this is rx. So the Pythagorean theorem would be r squared equals rx squared plus ry squared. So from here, you can easily find r will be square root 2 rx squared and ry squared. So if you plug these numbers in here in the formula, and you can find the magnitude of the vector, which is the same as here. Now finally, you may want to find this angle. Again, imagine this angle is not given, only these two components are given. How do you find it? Well, you could easily use sine, cosine, but in this example, because I know these two components, I can use tangent. So tangent theta would be opposite divided by adjacent. So it's going to be ry divided by rx. And if you do the calculation, you get 0.47. and take the inverse of that tangent by using your calculator, and you will find 25 degrees. So one caution here is that your calculator should be set to degrees so that you can get 25. If it's set to radians, then you will get some other number. The other thing that you have to know is you don't have to know, you don't have to memorize these. You can just look at the triangle, right? As long as you know tangent is, let's say this is y, this is x. As long as you know these definitions, you can easily calculate these quantities. So that was basically just a review of basic math, trigonometry, and vectors and components. So let's continue with another concept, which is called unit circle. Unit circle is very useful if you want to calculate like the angles sine 90, sine 0, 180, so these kind of angles. So think about a circle. It's called unit circle because its radius is 1. So here you get 1, you get -1, again, -1, -1. So this point, choose any point on the circle, and its components will give you, so the x component will be cosine theta, and the y component will be sine theta. Why so? Because if this is an angle theta, now think about this triangle. Okay, so the length of this thing here, the hypotenuse, is 1. Why? Because this is a unit circle, right? The radius is 1. So this part would be cosine theta. Why? Because this divide, let's call this question mark first. So cosine theta equals, it will be, remember from the trigonometry, question mark divided by 1. So it turns out that question mark is actually cosine theta, which is right. And this part is sine theta. Also, this point here is the value of the sine theta. Okay, this unit circle is particularly useful if you want to calculate sine and cosine of certain angles. Let's start with 0 angle. So this point is now at this point here. So what is sine 0? Well, sine is basically, so now this point. What is the y component? Remember, sine is the y component. What is the y component of this thing? You can think of this as a vector as well. Well, the y component is 0. That's why sine 0 is 0. And what is the x component of this vector now? Well, you can see that it's actually 1, and sine 0 is 1. Let's think about 270 degrees. Now, so the vector is now here. Okay, this angle here is 270 degrees. Now, what is the sine of 270 degrees? Well, the sine is the y component, remember, y component. So the y component is, this whole thing is, well, basically radius, so it's -1. What about the cosine of this point? Well, the x component of this vector is, there's no x component, so it is 0. You also have to remember that sine theta is cosine 90 minus theta. So in the question, you may be given sine 30 as 1/2, but maybe you need cosine 60. So if you're given sine 30, then you can actually find cosine 60, which will be the same thing, right? It will be 1/2. So you have to know these formulas so that you can use them whenever you need. Okay, so one warning about calculators. So you have to figure out if your calculator works with degrees or radians. So Now remember 180 degrees. So these are all units, right? This is a unit of degrees. 180 degrees is pi radians. This is another unit. See, number unit, number unit, number unit. And pi is approximately 3.14. I have to actually have an approximate sign here. Not exactly 3.14, but it's approximately 3.14 radians. Okay, so you can test your calculator. So if it's set to degrees, then if you enter cosine 180, then it will give you -1. But if it's set to radians, then only cosine pi will give you -1. Or you can try cosine 3.14 as I did here. This is actually a Google calculator. So cosine 3.14, it's almost 1, not exactly 1, because pi is not exactly 3.14. Now, in your calculator, you can actually switch between these two, degrees and radians. There should be a setting on the calculator which will let you switch between degrees and radians. Okay, let's talk about the components of a vector. So remember, a vector itself, it has a magnitude and direction. So a vector is the same with respect to all coordinate systems. Now, think about this coordinate system, x and y. So this is one coordinate system here. This is coordinate system 1. And there is x prime and y prime coordinate system. And the second coordinate system is here. Now, whether you have the first coordinate system or second coordinate system, or even I can even put my coordinate system here, doesn't matter. Does this vector r change if I change the coordinate system? No, the vector still points to somewhat in the northeast direction, and it has certain magnitude. And if I change the coordinate system, the vector itself doesn't change. Okay? But its components may be different in different coordinate systems. But the components do change. Now look at the x component of this vector in x, y coordinate system. The x component is this much. Now look at the x component of the same vector in the x prime and y prime coordinate system. Now the x, in that coordinate system, the x component is longer. But in this coordinate system, the x component is longer, but the y component is shorter. So that's why when you calculate, again, the magnitude of the vector r, you still get the same magnitude. So our x here is the x component of the vector r with respect to the xy coordinate system. And this one, our x prime, is again the x component of the vector, but this time it's with respect to the x prime, y prime coordinate system. So the components are different, but in different coordinate systems, but the vector itself is the same. Okay, we can also talk about the signs of the components. If you have a vector pointing in this direction, its x component will be to the right, so it's positive x direction, and y component will be negative, right, because it's pointing in the negative direction. So maybe this is -2, and maybe this is 2. So here the x component is positive, but y component is negative. If the vector is pointing this direction, then both components are negative. And if the vector is pointing in this direction, then y component is positive, x component is negative. And if it's pointing in this direction, so the angle between 0 and 90, then both components are positive. Okay, let's talk about now adding and subtracting vectors graphically. So there are two ways to add and subtract vectors. One of them is, the first way is doing that graphically, so on the graph. And the second way is doing it algebraically. So we will also see how to do it algebraically in the next slides. But let's start with this one. So let's say here the problem is let's say you start from this point and you go north for 5 paces. So you are here now, and you go to east for 3 paces, and you go this direction, southeast, for 4 paces. So you go first like this way, and then this way, and then this way. And the question is, what is the displacement? Now, remember, this is a 2-dimensional motion. In 2 dimensions, you have to use vectors. So you have to do a vector sum. How do you do the vector sum? Place the tail of the second vector to the head of the first vector. Then the sum, so the final, which is the displacement here, d vector, it will point from the tail of the first vector, which is here, to the head of the last vector. Okay, so let's do it here again. So 5 units to the north, and then the second vector, I'm going to add them head to tail, and then the other vector like this. Okay, so the displacement is, it's going to be from the initial point to the final point. So just draw a vector. I'll draw it thicker. So this is the displacement vector. So what we're doing is a plus b plus c. And it doesn't have to be displacement. It can be any vectors. It could be velocities, or the wind speed, other stuff. So it's just an example about vectors. Now you may ask, do we have to sum them in this order? Can we do, for example, b plus a plus c? The answer is yes, and it will give you the same vector. Let's do it. So I'm going to start with b. So this is my initial point, okay? So this is b, and I'm going to do now a. So a is, I have to add it like this. Okay, so this is b vector, this is a vector, and what's left is c. It is somewhat in this direction. This is the c vector. Okay, now what I'm going to do is, so this is the final point. So from initial point to the final point, I have to draw a vector. Let me make it thicker. And you can notice that this vector is actually the same as the vector that we found before. So this exercise show you that this order does not matter. So you can do the summation in any order. The only rule that you have to use is you have to place them head to tail, and then draw the final vector from the initial point to the final point. Okay, so we did adding the vectors. Let's do now subtracting the vectors. So subtracting vector b from a. So here's the vector a, here's the vector b. Okay, so if I put them head to tail, then it will give me a plus b. But how can I do a minus b? So subtracting vector b from a is the same as adding negative b to a. So I can write a minus b as a plus minus b. So what I have to do is, the rule of subtracting is basically, now instead of b, I have to find the negative b, which is in this direction. So this is negative b. Now I'm going to do a plus negative b. So a plus negative b. So I will basically add this vector here and this vector here. So a vector is like this, and then I'm going to add with this negative b, which is in this direction. Now this was the initial point, this is the final point, so I'm going to draw my final vector, and it will give me the vector d. So d is actually a minus b. Okay, so we did graphically. Now let's do it algebraically. Let's say you are given a vector a like this. So this could be some number, could be 4, this could be -2, and you are also given b, and it has the x component and the y component. Now, how do you add them? What is a plus b? What you do is you add the x components together, so ax plus bx. So you add them together, and then you write x hat. Remember, this is the vector part. And then you add y components together here, and then you write y hat. Does that make sense in terms of addition? Yes. Now remember, we used the add in the previous slides graphically. So a plus b would be this c. Now look at the components. The x component of c. So the x component of c is here. Okay. This is the x component of the c. So it is this whole thing, right? X component of c is actually x component of a, which is this part, plus, and this is b, x component of b. This is bx. So if you add these up, ax plus bx, you actually get the x component of the c vector. So graphically or algebraically, they are the same thing. So depends on the problem, which one you have to use so if you have if you're not given any numbers, just the vectors on a graph, then you would add them up graphically. But if you are given numbers and the vectors, if the vectors are given, if the components are given, then you could easily also add them up algebraically. But remember, when you have a vector on the left-hand side, you have to have a vector on the right-hand side. Now, who are the vectors on the right-hand side? X hat and y hat are the vectors. Okay, so now let's move to multiplying a vector with a number. So if you, let's say you are given this vector, a vector, 3x hat, 2y hat. So what kind of vector is it? It's 3, it has x component 3 and y component 2. So it's a vector somewhat in this direction. This is a vector. If you multiply it by 5, what you do is you basically multiply each number here. So you multiply the components. So 3 becomes 15, 2 becomes 10. So multiplication doesn't change the direction, right? Because now you can see it here. If you have the vector here, then multiplication, let's say multiplied by 3, since you are multiplying both components with the same number, its direction doesn't change, but it becomes just a longer vector. Or if you multiply by a number which is small, between 0 and 1, then you would get a smaller vector. And if you also multiply by a negative number, then you would get a vector which is exactly in the opposite direction. So now look at the ratio, 3 to 2, right? And look at the ratio here, again, 3 to 2. So multiplying a vector with a number does not change its direction, it just changes its magnitude, which is the length. Okay, so the position vector, let's talk about position vector. It points from the origin. So now we have the coordinate system. Now we have a particular definition, position vector. Position vector uses the origin of the coordinate system. So it is the vector that points from the origin, which is this point, to the location of the object. So let's say initially there was, let's say, a person here, and that person walked up here. So the position of the person initially will be this vector, our vector sub I initial, and the final position would be this vector. Now, if you want to calculate displacement, then what you do is you basically do final minus initial. But remember, now you have to do the subtraction as it should be the vector subtraction. So because now these are two-dimensional vectors. Now, let me give you an example. Let's say our I is 4x hat, 2 y hats. So it could be, so this point could be 4. So this point could be 4. And let's say this point is 2. And then finally, that person moves to coordinate system, the coordinate point 2, 5. This also means the coordinate point 2, 5, right? And this means the coordinate point x, y, 2, 4, 2. So for this one, this is 2, 5. Okay, this point and this point. Now, if you want to do subtraction, so we are going to do final minus initial. We only subtract the same component. So this is going to be 2 minus 4, which is negative 2 x hat, and 5 minus 2, which is 3. This should be 3 y hat. So this is the displacement. Now look at the signs. Its x component is negative and y component is positive. And it makes sense, right? Look at this vector here. Look at this vector here. Its x component is pointing in the negative direction. That's why you have the negative sign here. And its y component is, so this would be the y component. Y component is pointing in the positive direction. So that's why we get a positive sign here. Okay, so now we learned how vectors work. Now we can talk about how we can apply them to kinematics. So now I'm going to show you some plots, and these plots are not YT or XT graphs, okay? So these are not XT plots, but they are XY plane. So this is basically the two-dimensional plane. So you can think of this as, let's say, east, and it could be east, and this could be north. Okay, so imagine a person or a car or bicycle. It has this path. So it's moving, following this path. Now, how do you calculate average velocity? Average velocity is change in position, which is displacement. Now we have a vector because we are now in 2 dimensions, divided by the total time. So initial position is here. Okay, final position is here. Now, from initial position to final position, that vector gives you the displacement. So you have to find this vector. And when you divide it by the time, then the thing that you get is basically a vector which will be in the same direction with delta r. But of course, because you divide it by some number, it will have a different magnitude. It will have a magnitude different than delta r. But it should point in the same direction with delta r. Why? Because when you multiply a vector with some number or divide it by some number, delta t is not a vector, it's just a number, you still get a vector in the same direction but with different magnitude. So in this case, this would be the average velocity vector between points P1 and P2. Of course, for different points, the average velocity vector will be different. If you go from, let's say, P1 to, let's call this point P3. If you go from P1 to P3, then this is delta r vector, and the average velocity vector will be in the same direction with delta r again, but it will have some different magnitude because you are dividing it by some number. Okay, what about instantaneous velocity? Now, in the previous chapters, when we talked about instantaneous, we talked about the tangent. So the instantaneous velocity vector is tangent to the path. Instantaneous means right at that moment. So The question is, what is the velocity of the object? It could be a car, it could be a person riding a bicycle. The velocity at this point, now imagine, you draw a tangent. So that tangent line, it gives you the velocity at when you are exactly at this point. Again, this is not, there's no time, this is x direction, this is y direction. We are on the two-dimensional plane. So for example, what is the velocity at this point? Instantaneous velocity vector, it is in this direction. So you always go by the tangent. At this point, it's in this direction. And if you have a car going in circles with constant speed, so the constant speed means, let's say on the speedometer, you see 50 kilometers per hour. So the speed is constant, but the velocity is changing. Why? Because the vectors, remember, vectors have two things. Vectors, they have direction and they have magnitude. If one of these change, both doesn't have to change. If one of these change, direction or magnitude, then the vector itself is changing. The magnitude is the same. You can see the length here is this much. You can see the length is here this much. So maybe the speed is 50 kilometers per hour. But because it's going in circles, what happens is the direction of the velocity is changing. At this point, again, the tangent is like this. At this point, it's down. At this point, it's this direction. So because the direction is changing, the velocity is also changing. And again, it's the tangent to the curve. In the next chapters, we will see that if velocity is changing, there should be some acceleration. In this case, there is some acceleration actually towards the center of that circle. And when we do forces, when we learn about forces, we will see how that acceleration arises. Now, finally, let's talk about average acceleration. Now, remember, velocity is change in displacement, and acceleration is change in velocity. So here, again, the velocity is changing. The speed is the same, 50 kilometers per hour, but the velocity is changing. Why? Because the direction is changing. So there is some acceleration here. In fact, there is some force, and if there, whenever there is acceleration, there is some force. There is some force all the time that pulls the car to the center so that it goes in circles. And that force, we will see that will be related to, turning the wheel and acceleration and all that. So we will calculate those things in the in other lectures. So the average acceleration is average acceleration vector is in the same direction, in the direction of the change in velocity. So let's say initial velocity vector is this, and the final velocity vector is this. Okay, remember, how do you calculate v final? So that this means v final minus v initial vectors. So I'm going to do v final minus v initial. But with vectors, I don't really know, we don't really have a rule for subtraction, but what we can do is v final plus minus v initial. So if I find the inverse of v initial, so let's find it. If this is v initial, then the inverse is in this direction. So this is negative v initial. So I'm going to add this with v final so that I can find v final minus v initial. V final is this thing. So I'm going to add, I can add v final here. This is v final. So when I add them, what I find, this is the initial point, this is the final point. So draw this vector. So this is delta v vector. Okay, and you can see it here. And if you divide it by some times some number, you will get another vector, which will be average acceleration vector, which will be in the same direction with delta v, but its magnitude will be different because you divide it by delta t. So it's interesting, when you go on a path like this, you actually have an acceleration in the down direction. So you are actually accelerating, not, let's say, not down, but in the negative y direction. Or you can think of this as, if this is a circle, you are accelerating towards the circle of, towards the center of this circle. Okay, so we learned about this. Instantaneous velocity vector is always in the direction of motion, which means the tangent to the path. Now look at here. The velocity is tangent to the curve at that point. Here the tangent is like this. At this point the tangent will be like this, so the velocity will be like this. And at other points you can see the tangents. Of course the magnitude will be different, but from the curve, from the tangent, you can find the direction. But acceleration vector can point any direction depending on the force at that moment. So let's say initially your velocity is in this direction, but by just looking at the velocity, you cannot really tell which direction the acceleration is. Why? Because you may be going in this direction, but let's say in the car, but you can be speeding up. So in that case, the acceleration would point in the same direction with the velocity, or you may be pushing on the brakes and slowing down. In that case, the acceleration would be in the opposite direction to the velocity. Or you can be, you may be turning the wheel, and there may be, forces due to friction, and those forces may create acceleration towards the center of this imaginary circle. Oh, that's also possible. So the point here is, acceleration may point in any direction. Acceleration is related to force, so you cannot really tell by looking at the curve which direction the acceleration is. You can only tell by looking at the curve the direction of the instantaneous velocity, because it's basically the tangent. You can also, of course, if you remember from the previous slides, you can also talk about the direction of the average velocity as well. Okay, now as we are slowly moving into motion in 2 dimensions, let's remember our equations. So if you have 2 dimensions, then you can write our equations for both x and y dimension. So it's interesting that even though, let's say, you may have an object, this is x direction, y direction. So maybe an object is thrown this way, so it follows it's a projectile motion. So it follows this path. It's a 2-dimensional path, okay, something thrown up with some angle. But I can analyze this motion, I can make calculations by using 2 equations. One of them is for y and separately, and the other is the equation for x. The equations look the same, except only the instead of x, in the other one you have basically y components. So for the x, you have initial position at x. For y component, for y-axis, you have initial position y0. Here you have the x component of the initial velocity. So let's say this is your, let me draw it larger. So you throw something with some initial velocity, v0. It's a vector, right? Because it's 2-dimensional. So that object goes like this. This is x. This is y. So v0 has an x component. It's v0 x. Its magnitude is v0 x. And it also has y component. And that component is here. v0 y. Of course, time doesn't have any components. Its time is the same in both equations. And you also have ax and ay. So it's basically the acceleration x component and y components of acceleration. For this particular problem, if you have a projectile motion, the only acceleration is gravity, right? G. So the only gravity is A equals negative 9.8 meter per second squared. And it's A sub y, because there is really, for this particular problem, there's really no acceleration in the x direction because there's no force. So we would not have this part for this problem. But in general, of course, if there's a, let's say if there's a wind in the x direction, then there will be also A sub x as well. Now, these two equations, we can also write them as one equation in the vector form. So now, these are scalars, these are just numbers. There's no vector in these equations, right? But if you write it as a vector equation, it will be like this. The position at time t. This is the position r sub 0 vector, initial position. So let's say this is x, this is y. So the object is initially here. It moves to this point finally. So the initial position is r0, and the final position is, it's basically this r. This is the final position, or the position at, this is also, you can write it as well like this, the position at time t. This is initial velocity. Of course, it has x and y components. So if you want to write it, if you expand the components, it's x component times x hat, y component times y hat. Also, you can write the acceleration like this. Initial position could be written like this in the vector form, and the final position, or the position at time t, can be written as this. Now, if you look at, for example, the x components only here, so look at the x component. Look at the x component for initial position, initial velocity, and the acceleration. They actually all give me this equation right here. And if you look at the y components of this equation, it gives me the second equation for the equation for y. So you can use either of these, these two equations for x and y, or you can use this vector equation, just one equation for, depending on the problem. So let me give you an example where you can use this equation, the second one. So the problem is this. A particle initially at the position 03. So our particle is at this coordinate point is 03. So it starts its motion with initial velocity, and initial velocity is given here. So it moves in this direction. So it has the initial velocity in that direction. It doesn't mean that the particle will go in this direction. We will see that it's actually not going to go straight in the x direction, because there is some acceleration in some other direction. And again, remember, when there's an acceleration, that means there's actually a force in that direction. So imagine this, you want to go in this direction, but there's some wind in that direction. If you want to try to walk, you aim to walk to the right, but because of the strong wind, what will happen is you will actually go maybe in this direction. Okay, we will see the final direction in a couple seconds. So we have the initial velocity, we have the initial acceleration, and remember, in these kinematic equations, the acceleration is time independent. So the acceleration doesn't change with time, okay? the only thing that changes with time is this r and v. So v0, r0, they are time independent. A doesn't change with time. If you remember from the earlier chapters, in kinematics, we will be dealing with constant acceleration. So the acceleration is constant, so it will not change. But of course, velocity at time t and position at time t will change. Now the first question is, what is the position when 2 seconds passes by? So what I'm going to do is I'm going to use this equation. So the position at time equals 2 is, now I have to write the initial position. Now you have to be careful because we are dealing with vectors here. So whatever I write here, initial position is not 3. Initial position is, it's a vector from origin to the initial point. And this vector, it has no x component, and its y component is 3. So basically the initial position vector is 3y hat. Okay, so 3y hat, if you see something like this, don't say, okay, where's the x hat? Well, x hat is here, but it's multiplied by 0. And if that's the case, you don't have to write it. So you can just write 3y hat. So this is going to be 3y hat. This is initial position. Now, what about the initial velocity? Again, remember, this is a vector. I have to write this vector. Now, if you are wondering where is y hat, well, it is here, but it's multiplied by 0. So you don't have to write it. So it's going to be 5x hat. And I'm going to multiply it by time, which is 2 in this problem. And 1/2 acceleration. What is acceleration? X hat, y hat. What is the meaning of this? Where are the numbers? Well, the numbers are here. They are just 1. And if they're just 1, again, you don't have to write them. I'm not going to write them, so I will just write it as x hat plus y hat. And then t squared, so it'll be 2 squared. So the vector r, which is the position. So let's see what is x. So I have 10x from here, and I have 2x hat from here, like 4, 2, yes, 2, 10. So it's going to be 12x hat plus, what about y? From here I have 2y, from here I have 3y, so it's going to be 5y hat. So that's the position. Now, where is this position? Well, that position is, it's not, see, initially it was here. Now it's in 12x, so in x12, I don't know, let's say somewhere here. And in y, it's not at 3. It actually moved up a little bit. So instead of 3, maybe it's 5 is here, maybe. So it actually moved from here, initial point, to this point, final point. Now, even though the initial velocity was pointing to the east, it did not completely go, exactly went towards east, but it went towards northeast because there is some acceleration in this direction. Okay, what about the velocity at time equals 0? Easy, I'm going to use this one. So velocity at time equals 0 will be initial velocity, which is 5x hat. And what is the acceleration? X hat plus y hat times, well, now just multiply by 2. Okay, how many x hat do I have? 5, 2, so 7x hat. Plus, how many y hat do I have? 2 y hats. So that's the velocity at time equals 2 seconds. Now look at the velocity. Initially, it didn't have any y component, but at 2 seconds, the velocity has a y component as well. So initially, it was just like this, but finally, the velocity is something like this. Velocity at time equals 2. Okay, what about the speed at time equals 2? Now, speed is, velocity is a vector, speed is a scalar. Speed is scalar. That means it's just a number, doesn't have any direction. So how do you find the speed? Well, it's going to be the magnitude of this velocity vector. Now, how do you find it? Well, v equals, remember from the Pythagorean theorem, so 7 squared and 2 squared. It's going to be square root of 53. So we actually found the speed, the magnitude of the velocity. So it's 50 square root 53. And it is something like 7 point, you can use your calculator to find it, 7 point something. Okay, it's actually 7.3. Okay, now finally in this section, we will talk about relative motion. So the motion is relative if you are moving on some object. It could be a car, it could be something else. We can talk about your speed with respect to the car and your speed with respect to the ground, right? So let's say if you are in this car, if you are this person here driving, okay? So you have a speed with respect to the car, with respect to the truck, right? So your sort of speed of the person or the velocity with respect to the truck, what is it? That speed is 0, right? You are not really moving with respect to the truck, so that will be 0. But your speed, velocity, person, with respect to the ground would be the speed of the truck, right? V truck. That's right, V truck, with respect to the ground. Why? Because whatever truck has velocity, you have the same velocity. So if you're driving with, say, 60 miles per hour, then that means your speed is 60 miles per hour. So if you just, let's say, the truck disappears suddenly, that means you would continue going with 60 miles per hour. Of course, you're going to fall down and there's going to be friction, but I think you get the idea. Now, what happens in this image? Let's talk about this. This is actually from Mythbusters show. So what happens here is there is this truck. It moves with velocity 60 miles per hour to the left. It's negative because I chose that direction to be negative. So the velocity of the truck with respect to the ground, maybe I can put x hat here. So it's a negative x hat direction. And let's define my coordinate system like this. So the speed of the truck with respect to the ground is 60 miles per hour. Now you have a cannon here, and this cannon shoots cannonballs with speed, again, 60 miles per hour. So let's say the cannon shoots a cannonball. Now that 60 miles per hour is the velocity of the cannonball with respect to this cannon, right? Or with respect to the truck, because they are connected. Now what happens if you do this experiment? And you can see here, the cannon is fired, so the truck is moving with 60 to the left, and the cannon is fired with 60 to the right. But because these cancel out, exactly what happens is the speed of the cannonball with respect to the ground is 0. Okay, let's see how that works with the formulas. So let's say there's a train here, and there is an observer on the ground. So there's this passenger here. The passenger is walking with 1.2 meter per second speed with respect to the train. So if you ask the passenger doesn't look outside. he says, I am walking with 1.2 meter per second, the passenger, with respect to the train. Now, what about the train speed with respect to the ground? Now, the train, T is for train, G is for ground. The train is moving with 15 meters per second with respect to the ground. Okay, now the question is, so what is the velocity of the passenger with respect to the ground? Now, we talked about velocity of the passenger with respect to the train. And we talked about velocity of the train with respect to the ground. But the question here is velocity of the passenger, not with respect to the train, but with respect to the ground. So that velocity will be the velocity this observer on the ground will be observing. How do you do it? Well, this is the equation. So velocity of the passenger with respect to the ground is, remember, these are vectors. Velocity of the passenger with respect to the train plus the vector v, velocity of the train with respect to the ground. And in the next slide, you will see the calculations. Okay, so for this one, so I'm going to add PT, VPT, and VTG, right? VPT and VTG. And if I add these two velocities, it will give me the velocity of the passenger with respect to the ground. Now, what is VPT vector? It's 1.2, so this 1.2 times x hat. Why do we have x hat? Because this direction is the positive x direction. So that's why we have x hat. And I have to add now the velocity of the train, which is here, which is 15. Again, it's also in the same direction. Its direction is plus x hat. So plus 15 x hat. And what we found, the final answer is 16.2 x hat. Of course, everything happens in the x direction here. There's no velocity or movement in the y direction. So that's why everything is, that's why we don't have y hats here in this problem. And it makes sense, right? If the person is moving with respect to the train with 1.2 and the whole train moves with 15, then the person on the ground, the observer on the ground, will see this person as moving with 16.2 in the positive x direction. Now, what happens if this person moves in the opposite direction? Well, this is 1.2, but it's in the negative x hat direction. So you have to add a negative sign here. And then the train direction is again in the positive x direction. So you would write 15 x hat. Now if you add these up, so it will be 13.8 x hat. This is what this observer on the ground would see. So it's passenger, velocity of the passenger with respect to the ground. Now, let's go to another extreme. Let's say this passenger is actually walking with 15 meters per second in the opposite direction. Okay, think about it. The passenger, so 15 is the velocity of this passenger with respect to the train. So he's moving with 15. Now, if the train was not moving, you would say the passenger is moving to the left with 15, right? But what happens if the train is also moving with 15 in the opposite direction? So it will be negative 15 x hat plus, for the train, 15 x hat, and you will get 0. Just like with the cannonball. So this observer, so this person here, the passenger, even though he is walking with respect to the train, he would actually stay at the same point with respect to this observer. So they will be here. Both of them would be in the same position in this case. So now, so we got this formula from the previous slide. And remember, these are vectors, right? So this formula works not only in one dimensions, we did in the previous slide for a problem for one dimensions, but it also works in two dimensions as well, because it's already written in the vectorial form. So how does it work? Let's say this passenger now is climbing up. So this is passenger, the velocity vector of passenger with respect to the train. And the train is, with respect to the ground, is moving to the right. Now, what will the observer on the ground see as the velocity of this passenger? Now, if the train is here, let's say, let's do it this way. So there's an object here. It's climbing up, okay? So initially this object here is here. Let's do it this way. So initially, instead of the person, let's think about this object. It's here. Now the train will move. So the train will move here, this much. And in the meantime, this object, it's climbing up, right? So this is the edge of the train. Now the new position for the edge is here. And this object is always on the edge, but it's climbing up. Now it's here. Now, as time passes, the train now has moved here. Now, this is the train. Okay. Now, the object, again, this is the edge. It's just moving up, right? So if you ask this object, in this case, this person, what are you doing? He would say, I'm just climbing up, not going right or left, because he would be speaking with respect to the train. But for the observer on the ground, now look at it. You are like the observer on the ground. You actually see this object moving in this diagonal direction, not just up, but in that diagonal direction. So this equation, it also works with two-dimensional vectors. So now look at here. This is the velocity of the train. It's going to the right. And the passenger with respect to the train, he's climbing up. He says, I'm just climbing up with respect to the train. I don't know what's going on the ground, but he would just say, I'm climbing up. So his velocity is with respect to the train up. But if you add these two velocities, what happens? If you add this one and this one, they are already head to tail. So this is initial, this is final. You will get the final velocity like this. And what does the addition give you? It gives you the velocity of the passenger with respect to the ground. So this is the velocity as seen by the observer on the ground. And remember, the object, so this man, according to the observer on the ground, will be moving this way. Well, actually, with respect to this, let's say, he will be moving in this direction according to the observer on the ground. So depending on the problem, you may be given, let's say you need PT, but maybe let's say you need TG, but maybe you are given GT in the problem. What do? How do you find TG? Well, you just multiply by negative sign. So if you multiply by the negative sign, a vector, the indices, they just flip. So V train with respect to the ground is equal to negative V ground with respect to the train. Now, what is ground with respect to the train? What is that velocity? Well, let's say you are on the train or in a car. Now, the velocity of the ground with respect to the person in the car, with respect to the you, will be moving in the opposite direction, right? When you look at the ground, it looks like the ground is moving in the opposite direction. Okay, and finally, also notice the pattern in the subscripts or the indices in the formulas. So you have PG, so P goes here, and G goes here, and then between P and G, you get two T's. So velocity of passenger with respect to the ground is velocity of passenger with respect to the train, and plus velocity of the train with respect to the ground. And we can generalize this. It doesn't have to be passengers and trains. It could be water. It could be a person on a boat. So other things. So you can generalize this as these indices as 1, 3 will be 1, 2, 2, 3. Okay, here is 2 short questions. If the speed of the water in a river is 3 miles per hour, okay, let's say this is the speed of the river. The river is 3 miles per hour. How much distance would you go if you swim upstream? Upstream means in the opposite direction to the river with 3 miles per hour. Well, if the river is 3 miles per hour, let's say to the left, and if you swim upstream to the right, well, 3 minus 3, you would get 0. So you would not move at all. So even though you are actually swimming here, so if I ask you, what are you doing? You would say, with respect to the water, I am actually swimming with 3 miles per hour, but a person on the ground, on the shore, would see this person swimming, but not moving, but staying at the same point. Now, question 2, how much distance would you go if you swim downstream with 3 miles per hour? So the river speed was 3 miles per hour, and you also swim 3 miles per hour. Okay, so what is your total speed with respect to the ground? The total speed is 3 plus 3, so 6 miles per hour. And you swim for half an hour. So the distance, how much distance do you go? So it's going to be 3 miles per hour times, what is the time? 0.5 hours. So hours cancel, and the distance that you go will be 3 miles. Okay, this is the final question that we're going to do in this video. So you have a boat, and then you start from here and you aim in this direction. So that's it makes 25 degrees with the x-axis, this direction. So your boat aims in this direction, but the water flows down in this direction with some magnitude 1.4. Now, even though you aim in this direction, you will not end up here. What will happen is, because of you will get drifted by the water in the down direction, so in the negative y direction. So what will happen is, you will actually, because you will get drifted, you will end up here. So again, you set out aiming this point. If there was no water speed, if the water, instead of river, if it was a lake, you would start from here and reach this point if there was no water speed. But because water is flowing, you will get drifted along the way, so you will end up at this point. And this point is actually the velocity of the boat with respect to the ground. So it is the point that is aimed by the velocity of the boat with respect to the ground. Let's look at the indices again. So B is for boat, W is for water, and G is for ground. So velocity of the boat with respect to the ground. So if I ask you, what is your velocity? You would say, my velocity is 6.1 in this direction. That makes 25 degrees with the x-axis. Because if you're in the boat, you can only talk about your velocity with respect to the water. Okay, and the water velocity with respect to the ground is down, and it's 1.4. Now what's left? What's left is the velocity of the boat with respect to the ground. So here, if you want to compare this with the previous example with the train and the man, so ground is the ground, okay? Water would be the train, and the boat would be the passenger. So the same thing. Now, in this question, it asks, what is the velocity of the boat with respect to the ground? So we are, again, going to use this formula. So BG, B is here, G is here, and what's between is water. Okay, so velocity of the water with respect to the ground, let's write it down algebraically. It's purely in the negative y direction, right? So it will be negative 1.4 y hat, which we have here. Now we can calculate the velocity of the boat with respect to the ground. Let's calculate it. Now what I need is first velocity of the boat with respect to the water. So it is okay, we are not doing actually this yet. We got this part. So this part is negative 1.4 y hat. Now we need this part, velocity of the boat with respect to the water. So it's given 6.1 in some direction, but we have to write this as a vector here with x hat and y hat. So the magnitude here is 6.1. And then imagine you have a triangle like this. So this is 6.1. And this is the x component, and this is the y component. If this is 25 degrees, then this will be, remember, 6.1 times, because this is the opposite of the angle, you use sine 25 degrees. And for adjacent, you use cosine, 6.1 times cosine 25 degrees. So I'm going to have this here, and I have to multiply by x hat because I'm writing the vector here. And for this one with the sine, I'm going to write it with y hat here. Okay, if you do these multiplications, you can use a calculator. So this turns out this vector here, the velocity of the boat with respect to the ground, it has components, x component 5.5 meter per second and y component 2.6 meter per second. Now finally, I can find the velocity of the boat with respect to the ground. So what I'm going to do is I'm going to have this vector here and add it with this negative 1.4 y hat. So 5.5, 2.6, remember this is this vector, velocity of the boat with respect to the water. And this part is the velocity of the water with respect to the ground. So if you do the addition, well, you know, there is x component is the same. These are y components, so you subtract them and you get 1.2. So the final answer is velocity of the boat with respect to the ground. It has 5.5 in the x direction and 1.2 meter per second in the y direction. So in this problem, the angle is given, and what the problem is asking, the velocity of the boat with respect to the ground. Okay, let's think about the case where the angle is not given, and in fact, if the question asks you what the angle is. So let's go to the next slide. So in this case, the angle is not given. So the question is, what should be the angle so that the boat sets out from A and directly reaches B? So what I want is the boat starts from here and it still aims at some angle in this direction. I don't know what that angle is. We're going to calculate it. But so on the other side, I want it to reach exactly at this point. How is that possible? So you can think of maybe this way. If you aim in this direction with the boat, now if this is the boat velocity, boat with respect to the water, and there is some drift velocity because of the water, now finally you will go in this direction, right? That doesn't work. If you aim maybe this direction, and then if you add the water velocity, now what happens is the velocity of the boat with respect to the ground. This is velocity of the water with respect to the ground, and this is velocity of the boat with respect to the water. You control this, okay? And you don't control the water velocity, so you can control the angle and the speed, which is here. And the combination of these will give you your velocity of the boat with respect to the ground. But in this case, you will go this direction. That's not what we want. We want to go from A to directly B. So what you have to do is maybe you have to have some angle in this direction, that theta. And if the velocity of the water is exactly this much, so the velocity of the boat with respect to the ground will be exactly in, it will be due east, right? It will be in the east direction. So that's what we want. So basically what we want is the velocity of the water should be exactly opposite and with the same magnitude with the velocity of this. So this is, remember, this is velocity of the boat with respect to the water. It should be, so this water velocity of water with respect to the ground, it should be exactly opposite and with the same magnitude to the y component of velocity of the boat with respect to the water. In that case, the resultant, the final vector, will be exactly in the east direction, so that you can go from A directly to B. So the solution is when water speed, so water speed is this, and the y component of the boat's speed, let me show you here. So the y component of the boat speed is this. If this is equal to the water speed, there will not be any motion in y direction. So you will go right to be horizontally. So if these two are equal and opposite, then the boat will have no motion on the y-axis. So the motion will be purely on the x-axis. Okay, now what is this? This one is, so this was 6.1, the vector is 6.1, and this component would be 6.1 times, okay, so this is theta. Now this part is opposite, right? Or this part, so I have to use sine. So 6.1 sine theta. So if 6.1 sine theta, that magnitude, if it's equal to 1.4, which is written here, then the condition will be satisfied and there will be no motion in y, so the boat will go from A to B horizontally. So you have this equation. So you have to write it for, so sine theta equals 1.4. So I'm just dividing both sides with 6.1. So 6.1. And just take the inverse of it. So it will be theta equals inverse sine 1.4 divided by 6.1. And if you calculate it with your calculator, you will find the angle should be 13 degrees. So again, when the angle is exactly 13 degrees, you can go from A to B. If it's more than 13 degrees, if this is A, if it's B, let's say the angle is 15 degrees, you will end up here. If the angle is, let's say, not 13, but let's say 10 degrees. So if this is A, if this is B, so what will happen is you will end up down here. under B, not exactly at B. So that's all for this lecture.